No. Okay. So the first question that I want to address regarding how we solve congruences, let's think about this particular congruence, right? AX equals B or congruent to B mod M. How would we solve this? This doesn't have a general solution in the integers, and it won't have a general solution depending on the value of M. So maybe we can find a criterion, right? And this criterion will be important because it is one crucial part of, I don't know which question in your problem set. This is a very important part in the context of fields. As you know, some of these congruence classes form a field, and that happens specifically when M is a prime number. In that case, this always has a solution when A is non-zero. When A is zero, of course, this will not work depending on B, right? Because everything times zero is zero, even in the world of congruence classes. So how do we solve this? So let's just say, how would we discover this if we didn't already know, right? Because I know, but the thing we would say is suppose there is there's a solution. There is a solution. X. That means this is one thing you can always do, right? If you don't know how to solve something, why don't you pretend that it has a solution and try figuring out what properties that solution has? The more properties you add, the more restrictive it becomes. It should become easier how to find it because you have a big list of things it must satisfy, or that list might be too big and it contradicts itself, meaning there is no solution, right? So suppose there is a solution and let's see if we can find it, right? So this means that M divides AX minus B by definition. So what can we say? What can we say about this, right? So M divides that number. So what property can we derive? Actually, you know what? Let me just write down the theorem so that we are actually working in a more concrete direction. For the purposes of time. Am I recording? Yes. So the theorem is as follows. AX has a solution, sorry. A solution if and only if the greatest common divisor between A and M divides B. In the case where M is a prime number, this greatest common divisor is always 1, unless A is 0, of course, right? So when A is non-zero and M is a prime number, this will always be 1, and 1 always divides B. So this always happens when M is prime, meaning it always produces a solution when A is non-zero. But let's think about this in more generality. Why should this be true, right? So here is the proof. Suppose that this is the part I was writing down earlier, right? Suppose there's a solution. And that D is a common divisor. So it divides A and it divides M. If I manage to show that D divides B, well then every common divisor divides B, in particular the largest one, right? So if D divides A, so we know that M divides AX minus B. So how do we combine these facts? What do you think? What do you think we can say about this? Actually, we don't even need this. Well, there's a solution. Since the greatest common divisor between A and M obviously divides A and an M, divides A and M, then it must also divide this number that I just wrote down. Right, so the greatest common divisor between A and M divides A and it divides this number. So if I combine them, I should be able to get B, right? So let me see how we can combine them. AX minus B plus X times A minus x times a, which is minus b, or I have mentioned many times in the past that a number divides another one if and only if you can add plus minus on either side and it doesn't change that fact. So it must divide b as well, right? So conversely, if the greatest common divisor between a and m divides b, then how do we produce a solution? How do we find an x that has this aforementioned property? What do you think we can do in this case? If the greatest common divisor between a and m divides b, divides b, how would you find a solution x? So the idea, as maybe you figured out, is that if the greatest common divisor divides b, then by Bezoos identity, we can find, this is always the trick, right? When you have something that is co-prime or something involving the greatest common divisor and you need to do some calculations about it, you find integers and write this as a linear combination, right? So as plus mt is the greatest common divisor. Sorry, let me write this the other way around so that it becomes easier. Greatest common divisor between a and m is this. It's the least positive linear combination. We don't really care about the least part, and you can also use the extended Euclidean algorithm to argue why this is true. So what we do now, we reduce this mod m to get as, right? Now we also know, let me see what we're trying to get to. We want to show that this is equal to b, and we haven't used the fact that the greatest common divisor, this number on the left, divides b, right? So how would you conclude this last bit, right? We want to guarantee that this is equal to b. So any ideas? Did anyone think about this for the last couple of minutes? In the meantime, let me give you an important example that maybe tells you how to do this. Important example. Suppose that the greatest common divisor between a and m is 1. Sorry, is that what I want to write? Yes. So if these two are co-prime, then according to the theorem, this always has a solution. Ax equals b has a solution, right? So in particular, instead of b, I can just write the number 1, right? Has a solution. X is called the inverse of a mod m. Inverse of a mod m. And how do we find it? So to find it, use the extended Euclidean algorithm to find or compute a and m are co-prime, right? So a and m, one must be written as a linear combination of them. And again, I did the same mistake where I wanted to write these the other way around. Okay. Right, so one is a linear combination of these two. And if I reduce that last expression mod m, it cancels out the m and I just get a times s, right? So this is how you can find the inverse of any number mod m if it exists. If it doesn't exist, well, you would also figure that out by reducing this using the extended Euclidean algorithm, because you would find that the greatest common divisor is not 1. So this will not have a solution because the theorem is an if and only if, right? This is how you find the inverse of any number, and it is perhaps the most important application of the extended Euclidean algorithm. And more examples of this will follow. Okay, so how do we conclude this last bit, right? In the case where the greatest common divisor is 1, then this was easy to do because 1 always divides b. But what would you do in this case? So where does the b come from? Any ideas? Okay, why don't I leave this last bit as an exercise, and if you don't figure this out in the next minutes, I'll tell you how to do it. So where does this come from? Exercise. How do we conclude from here? And again, the hint is I haven't used the fact that the greatest common divisor between A and M divides B, right? So A and M, sorry, the greatest common divisor has this property. Okay, in the meantime, let's look at something a little bit more sophisticated. And just to help you out with the problem set, a consequence of the theorem that I just proved is that Zm is a field if and only if. I'm always tempted to write the arrow, but I think this is better. If and only if M is prime, right? So the proof of the corollary is part of the problem set. Problem set 3, I guess, right? Because this is we're talking about fields here. Let me give you a slight generalization of the thing that I just mentioned. And maybe one more example. Example that should make this corollary easier because it's the same idea, right? So if m is 6, well, this is not prime because you can factor it as 2 times 3. Then how do you convince yourself that this is not a field? So the reason is that 2 is not invertible. 2 has no inverse. Mod 6, right? 2 times 3 mod 6 is 6, which is 0. So you can find two non-zero elements whose product is 0. Okay. We can also check this as just doing it by cases. There's only 6 possibilities, 5 of which are non-zero. So out of those 5 possibilities, none of them is going to be the inverse, right? Okay, and of course this seems like a dumb example because it's a small number 6, but in general, if you have a number that is not prime, so composite, then you can find two factors the same way I found the factors 2 and 3, and you can multiply them together and get 0 mod that number, right? So this idea generalizes in a more abstract setting. Now let me give you a very similar theorem, and maybe I will write the full proof of this one without exercises. Here's another theorem. How do we combine two different congruences? Why would we want to do that? Because sometimes congruences with a very large number need to be broken down into smaller ones that are solved individually, and then the solution is put back together. This was done in the tutorial with a rather sophisticated example. And you can find the solutions with all the details posted on Quirkus in case you want to take a look at that. So the previous method, the previous theorem tells me that if I have a congruence of the form ax equals b, then I can reduce it to something of the form x equals, let's say, c, right? So the question is, how do we combine two of these simplified congruences when I have something of this form, right? This and let's say b. So this is a system of congruences. Now I have two congruences that I want to satisfy at the same time. and I claim that this system has a solution, it's the same method that we used previously, right? So if you know how to do this, you should be able to see how to complete the proof. But I will do that in a few minutes if you don't know how. So the only criterion that we care about is that A and B must be congruent mod the greatest common divisor between sorry, I should have picked different numbers here to make this even more general. So let's say NM, yeah. So this is pretty interesting. And this is known as this is like, maybe I should call this a lemma for the Chinese remainder theorem, right? Maybe we want to use this specific result and independently, right? So let's do this an if and only if statement. So suppose X is a solution, So what can we do? Well, there are two integers, s and t, that make this, in problem set 2, you prove that two things are congruent if and only if a bunch of equivalent things. So the one I care about now is this one, right? So x is some multiple of m plus a, and it is also, at the same time, some multiple of n plus b, because it is congruent to a mod m and congruent to b mod n, right? So I find the coefficients that make this work, and I have this situation going on here. Now this part might be a bit tricky, but the trick that I think works is you divide, so you subtract b from a, and if I do that, then I should get, let's see, a is tn minus sm. If I did this right, I solve for a, right? And if I solve for a, this is tn minus sm plus b, and then I just subtract b on both sides, and I get this thing that I just wrote down. So this is a linear combination of n and m, right? So the greatest common divisor divides every linear combination, including this one, a minus b. This is, again, a consequence or part of the proof of Bezout's identity. I mentioned this, that, I mean, we don't even need that, right? If a number divides, sorry, what am I trying to say? The greatest common divisor divides every linear combination of the two numbers because it divides each of those numbers individually. Actually, we could have used the same. This for this method might have been even a little easier. Okay. So this is a linear combination. The greatest common divisor divides it, right? And therefore, this is just the definition, right? This means that A is congruent to B mod the greatest common divisor of these two numbers. So this is the forward direction, right? Now let's look at the other one, conversely. And this should be very similar to the proof that I left incomplete, which is why I think it's acceptable for me to do so. Conversely, if this happens, I want to write all that thing down. If this happens, meaning A and B are congruent mod the greatest common divisor, then let's see. We use the same trick that I left incomplete in the previous proof, right? So it's the same situation. If you think about it, it's the exact same thing. So right here, the greatest common divisor is dividing a number b, and I use Bezout's identity. Well, here, the greatest common divisor is dividing the difference between two numbers, a minus b, right? So I use Bezout's identity to write. This is the trick that always works. And if in the final exam I happen to include a problem that talks about co-prime numbers or the greatest common divisor, stuff like that, then one of the things you should consider using is Bezout's identity, right? Because it is a shortcut. It makes a lot of things easier, and yeah, especially a lot of these elementary arguments. So let me see. greatest common divisor between n and m is, I don't know, let's say nk plus ml, right? And I also know that that the greatest common divisor divides a minus b. So this is the step that I am missing. This is the step that I skipped and left as an exercise, right? The fact that the greatest common divisor divides this number. How do you use that? So let me tell you how to use that, and you should be able to fill in the details, which I think no one has written out the details in the chat. So that's why I maybe want to leave it open for a little longer. Since the greatest common divisor between n and m divides b minus a, just apply the definition, right? There is c, an integer whose product with the greatest common divisor times c, and m is a minus b, right? Just multiply it times some factor, and you get that. And now you might be wondering, how is that useful? Because that's the thing I didn't mention. So here's how you use it. A minus b is equal to n times, let's see if I get this right. So you multiply this part times c, right? So this should be n times kc minus m times, I think I have to add another minus lc, right? Just plug in those two things. Substitute this in there and maybe move things around. Okay. From here, what if I just write a plus m minus lc, and put the b on the other side, right? So to put b on the other side, this is n kc plus b, and I'm done. Why am I done? Because this number, this integer that has two different representations, this integer, let's call this number, could be negative, right? Call this number x. So what is x when I reduce it mod m? And what is x when I reduce it mod n? Well, I need to use the different representations that I came up with for this to work, right? So let's see if I can get this in order, more or less. Minus LC, and it is also equal to n kc plus b. If I reduce this mod m, the m cancels out and I just get a. And if I reduce this mod n, the n part cancels out and I just get b. Oh, I'm done. X is indeed a solution to the system. So this feels a little bit like magic. And I think this is pretty cool, right? Actually, I may have forgotten to add this thing right here. Wait, where did I write this? Oh yeah. Okay, so the same trick will work for the proof I left incomplete, right? So make sure you see how to do that. And now, moreover, the solution, if it exists, is unique. There might be many solutions, but there can only be one mod the least common multiple of n and m, right? Before we do an example of this, let me tell you what this theorem, what this lemma is used for, and this is known as the Chinese remainder, which is known for a really long time. It's a very simple generalization of what I just wrote down. So this works for two congruences. The Chinese remainder theorem works for k congruences, right? And by the way, maybe I should leave this part of an exercise as well. But please, I will ask you on Monday or whenever our next lecture is, I will ask you if you solve these two exercises, because maybe they're not that simple and I'm happy to fill in the details. But I mean, they're also quite straightforward, right? So just let me know. So the fact that this solution is unique mod the least common multiple of n and m, that's left as an exercise. Okay, so let me think about why I need this. Sorry, before we apply the Chinese remainder theorem, before we state it, let's make one example so that this is clearer. And hopefully this is the example that I included as today's quiz. Example, let us solve the following system. Mod 21. These are just random numbers, right? So I don't know what the solution is going to be. And 19 mod 56. Let's solve this. Let's solve this together. And then you can just submit your answer, adding any detail that I wasn't clear about. So first, to know if this has a solution or not in the first place, the theorem says, well, take the greatest common divisor between these two numbers and see what happens, right? So we can either use the extended Euclidean algorithm, but these numbers are small enough that I can just factor them. 3 times 7 and 56. 56 is, what is 56? 7 times 8. Right, so the greatest common divisor is, of course, 7, using the trick that we did last time. If you want to be a bit more explicit with the primes, I did like this, right? So 7 is the greatest common divisor, and 5 is indeed equal to 19 mod 7. And 5 is indeed 19 mod 7, I hope. I picked these right. So there is a solution, a unique solution, mod the least common multiple, which is, of course, oh my God, something kind of horrible, right? 2 times 3 times 3 times 7. I don't know what the number is, but that's the least common multiple. I'm just picking out the way we did in class, right? I'm picking out the biggest exponents of each of these, and that gives the least common multiple. And for the other part, I'm using the smallest exponent, right? It's a criterion that I mentioned in, I think, last week, one of the lectures. So there is a unique solution. The question is, how do we find it? And before I give you a concrete method of finding it, there's basically two ways. So one is by brute force, which might seem like it's not a very good method, but for small numbers, it works even faster than the other method, right? So how do we solve this by brute force? Maybe let's do this first, and then I tell you how to solve it the other way. Okay. So solutions to, let's call this 1 and 2, these two different congruences, right? So what are all solutions to 1? Well, the solutions to number 1 are, there's infinitely many of them, but of course it's going to be 5, what, mod 21, right? It's the next one is 5 plus 21. It's all numbers that are 5 mod 21, right? So this is 26. And if I continue doing this, I get, I think, 47, if I'm not mistaken. Please let me know if you see a mistake here. 47, 68, 70, no, not 70, 89, right? Just keep adding 21 to get all solutions. 110, 131. And we can continue doing this. What are the solutions to the number 2? Well, 19 is, of course, a solution. 19 plus 50, okay, I'm regretting this already. 56 is 75. And 75 plus 56 is 131. Okay, I did this the right way. Notice that I found a match. I found a number that is a solution to both systems at the same time. So that must be the only solution, mod the least common multiple, right? So all solutions are of the form 131 plus some multiple of whatever this large number was, right? The least common multiple of 21 and 56. I don't really want to compute right now in its expanded form, but this number is equal to this number, right? It's the same thing. So that's how all solutions look like, and I have just solved the system of congruences and found all solutions to it. Notice I have no additional restrictions on n and m. The Chinese remainder theorem does have additional restrictions because it gets more complicated if I add more congruences, but I don't really need those in this case. So there's a more intelligent way of solving this, and I will start you off with the first few steps and expect you to write those up as part of today's quiz, and I will give you enough time to do so. So the idea is that since, let's see, which number is larger? Okay, it doesn't really matter, right? You usually want to pick the large number so that you reduce the small number, you get something easier to work with. So since x is congruent to 19, so this is another method. This is the smart method. So if you reduce this mod 56, was it? That means that x is equal to some unknown multiple of 56 plus 19, right? Then we can reduce all of this mod the other number, which was what? 21. And if I reduce this mod to 21, what do I get? 56 mod 21 is, let's see, 40, 42. And I get 8 plus 16, which is 14s. And I could just write 19 or minus 2, whatever feels more convenient in the moment, right? So this little part here is because of the second congruence. And now I have to use the first congruence because I want this. I want this to be equal to what? To 5? Was it? Yeah, 5. And this tells me, using the techniques I already developed, how to find S. And if I found S, then I found X. Because this is just a congruence, right? This part right here is a congruence involving just one number, the unknown number S mod 21. So you can simplify this and then quote unquote divide by 14 the way I just explained in the previous example and in the previous theorem to find S. And once you find S, any representative of S will work, then you know how to find X. And if you find a larger representative, you might not get 131. You might get a different number that is congruent to 131. But this is why all solutions are of this form, right? So completing this is part of the quiz. I already started you off with the most difficult part. So completing this, it's just a combination of the last two theorems. Completing this is today's quiz, which should hopefully be already online on Quirkus. Please tell me if that's not the case. So while you work on this, again, this is not supposed to be like a punitive thing where if you got it wrong, I punish you or something. The idea is that we all work through this together, right? So I will give you enough time to think about this and ask me questions. If you have no idea how to solve this, I will tell you. If you have no idea how to solve the previous exercises, I will also tell you. In the meantime, let me just write down the statement of the Chinese remainder theorem. And I don't think we will prove this because it's just applying the lemma inductively, right? We already did the hard part of the Chinese remainder theorem. So let me just write down the statement. Like I said, now I'm adding additional restrictions on the modules. Now they have to be pairwise coprime, right? So if M1 dot 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 MK are pairwise, pairwise meaning any two of them, any two different of them have a greatest common divisor of 1. That's what pairwise means. Pairwise coprime, and let's say I have a bunch of numbers, A1, A, K are integers, right? This is not the most general way of stating the Chinese remainder theorem, but it works for our purposes. Then there is x, let's say a unique, and by unique I mean mod the product times of all of these times the product x such that, and here's the magic, right? X is a solution to all these systems of linear congruences. So X satisfies that M sub I. I forgot the for all. For all I, X is congruent to AI mod AI. So X satisfies all of these numbers, all of these congruences simultaneously, which is pretty interesting. And the proof which I will not complete, but it is very straightforward, is induction. Use induction on K and the lemma. You have to use the lemma exactly twice. Once for the base case, which is K equals 2, because K equals 1 is trivial, right? K equals 1 is just the statement said twice, basically. K equals 2 is the lemma. And for the inductive step, you are going to need the lemma again by first simplifying a bunch of congruences and then adding the last kth plus 1 congruence, right? So induction on K and the lemma. And this is easy enough to be an exercise, but it could have been hard enough to maybe include this in the problem set, but I think all these techniques are being repeated, so that's why I didn't include it there. But this is an important exercise. So today I know I wrote down several not that easy exercises. So please try to think about these before Monday, and I will solve any ones that you couldn't solve, or ask on the platform as well. Okay, I will wait now for 5 minutes, maybe take a short break for you to complete the quiz using this method, right? This is the smart method. The smart method where you don't use brute force. The smart method. And I will not continue until you tell me if you have questions, if you have trouble submitting this. So maybe if you already finished this so that you don't get bored, I will show you a third method. It's not really a third method, it's just the same method but written slightly differently. So let me open up a console. If you're interested in computer science, then this will be of interest to you. And in the meantime, please let me know if you have trouble solving any of the exercises, particularly the quiz, which of course you need to submit today, right? Okay, I'm sharing my console and let me open up a Python terminal. And what I want to do is I want to solve the system of congruences, right? So let me see if I can do that in just one line so that you see how easy it is. Okay, so I want all the x for x in range, and the range is going to be the least common multiple because that's where I will find the unique solution. And the least common multiple is 2 times 3. I'm pretty sure Python associates the precedence of operators correctly, so I don't have to add parentheses there. Pretty sure about that. Let's see, 3 and 7, right? So times 3 times 7. So that's the least common multiple. That's the range I'm looking for solutions. And the condition that I want x to satisfy is the following. If I reduce it mod, what was it, 21? I should get 5. Let me double check if that is correct. Yes, and I also want this to be congruent to, what was it? 19 if I reduce it mod 56. So that should work, and it didn't work. Okay, give me 1 second. Okay, let's think about this for a second. I did find a solution, right? Oh wait, this doesn't make any sense. Sorry, I forgot a number. It was 2 to the 3 times 3. Huh. Okay, there we go. 131 is the only solution in that range. And if I remove the range, then you can see how the solution is unique mod that number, right? So if I add something, I don't know, absurdly large, maybe 1,000, then you can see that all these numbers are congruent to 131 mod the number I just wrote down, which I don't want to compute. I mean, if you really want to know what it is, I can just retype it. It's 168, right? So this is how you can solve any system of congruences instantly. But this is brute force. So this isn't the smart method, because Python is literally checking one by one, right? But there's a smarter way of doing this. Okay. Any questions about anything I've said so far? Hopefully I'm appealing to different people's interests here. Any questions or trouble with the quiz? There's one example of how you apply the Chinese remainder theorem in a bit more generality when the numbers are not necessarily coprime. This will not always work, but the method will work in case there is a solution, right? Okay, so let me add some more details about the Chinese remainder theorem, and I think that's all I want to cover for today. I maybe wanted to talk about Fermat's little theorem. The proof is short enough that I could cram it into a lecture, but I don't like doing that. Okay, so let me just rephrase what I just said. So in other words, the Chinese remainder theorem says that, if I want to write this in a different way, if I have a system of linear congruences, M1, A1, and then M2, A2, right? So I have a very big system, and these are already reduced. If I have a coefficient here, then I can cancel those using the methods of the previous lecture. So it is very well possible that I include something nasty like this in the final exam, something like solve 2 equals 3, 17, and a bunch of this. And this has two steps. First, you have to reduce the number 2, remove it, and find whatever inverse you get here, and then write it in the form of the Chinese remainder theorem, and then apply the techniques that I just told you how to use to solve this one, right? What letter do I use? K? Yes, K. AK, the system of linear congruences has a unique solution, always has a unique solution, right? Why does it always have a unique solution? Because if these are pairwise coprime, then the lemma says that the GCD is 1, and 1 divides everything, right? So this always works. But this lemma is a bit more general in that, as you can see, I'm not necessarily saying that these M and N should always be coprime, right? So this doesn't necessarily just work in this case. Now beware, if you're trying to solve something using online tools, I can give you an example of, if you Google Chinese remainder theorem solver calculator online, the first three web pages, and I only tried the first three, I'm pretty sure all of them have this problem. They might not give you the right answer if you change these things a little bit. So I will add a comment on that in a second. Has a unique solution mod the product, right? So M1 times M2 and so on, MK. So this number is basically the binary, could for example be the prime decomposition of a large number, because the powers of primes are always pairwise coprime. So if you have a very complicated uh, uh, linear congruence, then you can split it into smaller pieces and get something like this, and then use the Chinese remainder theorem to find the solution for each of those things and then put them all together. Okay, so I have a question in the chat. Okay, so the question is about the example I wrote down. How would I actually find the inverse of 2? Yes, okay, let's do that. Okay, so this is the other way of writing the Chinese remainder theorem. So here's a question that I was asked. The example I wrote down was this, I believe. Doesn't matter what number I find because number I wrote here, because if I find the inverse of 2, then I'm done. All I have to do is multiply that inverse, right? So let's see if we can solve this in general. How about I write B? And then we solve this. The way I didn't solve, I left this proof incomplete, left as an exercise. So how do we find the inverse mod 17? So let's do that, right? Let's do that. So the answer. The answer, the algorithm that always works is apply the extended Euclidean algorithm. That's always works. Some easier methods might work. For example, multiplying this iteratively or trying to find a larger number, right? For example, if this were the number 2, then I already know I can just cancel 2 on both sides. I already know that must be possible because I know the inverse exists even if I haven't found it yet. So that is one way of figuring out what x should be without finding the inverse explicitly. And that is also always possible. But let's do this in a lot more generality so that I answer the question. Okay, so how do we find the inverse mod 2? According to the procedure I described, what you have to do is take the number 17 and divide it by 2. So this should be 8, which is 16 plus 1. And oh, I'm already done, right? So the extended Euclidean algorithm stops immediately because I already found a remainder of 1. So the next step would have been if I take the number 2, sorry, this way, right? If I take the number 2 and I divide it by the remainder, last remainder, and then I get a remainder of 0, right? So this always happens, and this is why we skip this step because this is doesn't give us any information. Then if you write 1 as a linear combination of 17 times 1 plus minus 8 times 2, then what I do is I reduce this mod 17 so that I cancel out this one. This is just 0 plus minus 8 times 2. And you can see what the inverse is, right? This is minus 8 times 2. So I found a number that when multiplied times 2 gives me 1 mod 17. Thus, the inverse is minus 8. Now, minus 8 is a weird way of writing this, so typically people will say this is 9. We find a positive number that satisfies this. Is it 9, or did I mess this up? 2 times 9 is 18. Yeah, of course, it's 1 mod 17. So this was maybe a little easy, but you can find a more complicated example and the same procedure should work. Right? So the solution is you take x and you divide by 2 on both sides. And dividing by 2 in this context is the same as multiplying times 9. So the general solution is 9b. Right? Mod 17, of course. So this is how you can solve any congruence. Any linear congruent can be solved like this. Any combination of multiplication and addition can be simplified to this. Yes, you're welcome. This was a good example. Usually you will not be done in just one step, right? If you were done in one step, then you could have probably guessed the answer. But the Euclidean algorithm might go on for more steps, but it doesn't matter, right? It will provide you with this linear combination whose simplification gives you the inverse every time. This always works. And for large numbers, it's much faster than whatever other method might be out there. Okay, so there's 15 minutes remaining. I don't really want to. Is there something more I want to say about this? Let me just say this without writing it down. So the Chinese remainder theorem assumes that these numbers are pairwise coprime. If they are not pairwise coprime, there might not be a solution, but there might be a solution. And this is one example you have to be very careful in, because if you ask ChatGPT to prove things about this Chinese remainder theorem, it will assume that if they are not coprime, there is no solution. And the online calculators, actually, let me see if I can show you this because it's pretty cool. Okay, give me 1 minute to think about an example. of a linear congruence, a system that has solutions even though they are not pairwise coprime. Let me think about this. Okay, so let me write this in red as a warning. Warning. Be careful. When using online tools, calculators, slash ChatGPT. Unless you programmed this yourself and you know what it's doing, like I did with the console a few minutes ago. Here's an example. Okay, so I think this works too. Okay, now that I think about this, this might not be the example I want. 2 and 3. Okay, let me think about this. Wait, this is dumb. Of course, this is a very simple example. Has an obvious solution. X equals 1, of course, is a solution. Even though 2 and 4 are not coprime. Now, this example is easy because it falls into the same category as the lemma. It's just two congruences. But I mean, if you really wanted to, you could add more, right? 8, 1. You can add a bunch more. I don't know, 10. Doesn't really matter. So this one has an obvious solution, which is x equals 1, even though 2 and 4 are not coprime. None of these are coprime, and yet it has a solution. Now let me show you. Let me show you why this is dangerous. Maybe I can share my screen with you. So give me a second while you ponder about what I just said. This is the warning I'm telling you about. Let me find an online calculator and show you that it will not give me the correct answer. And ChatGPT, I'm pretty sure will also fail, even though I haven't tried it. I've tried with other examples. Okay, let me show you. Okay, I'm going to be a little embarrassed if this actually doesn't work, but let's just see what happens. Right? It's all about discovering these things. Okay, so I'm sharing my screen. This is my browser. All I did was Google Chinese remainder theorem calculator, and there's a bunch of calculators here. Let's try the first one. And let's see what happens. Okay, so here I have to put in the coefficients for the two equations, right? So the first equation, A1, is of course 1, and n in my example was 2, and the second equation was 1 and 4. Sorry, 1 and there we go, 4. I don't know why my computer's so slow. So this is the system that I wrote down. This has an obvious solution, which is 1. But the prompt that the result is saying is that it has no solutions because these are not coprime. So the calculator is correct to say that this might not have a solution because its method won't work if they are not pairwise coprime. But the answer is wrong, right? Of course this has a solution. X equals 1 is a solution. So why is it saying it doesn't have a solution, right? Do you see the problem, or am I just making stuff up? Let's try another one. This is the second one. Okay, so Chinese remainder theorem. Can I just type this? Oh, that's pretty cool. Okay, so x equals 1, and I can just add whatever I want here. Might seem like a dumb example, but my point with all this is that if you don't know what you're doing, you will not get a right answer using these tools. Okay, so GCD is not 1, so the given equation has no solution. It isn't true. 1 is a solution. 1 is a solution to both. And you can say everything you want. You can even find out that solution is unique, mod, whatever, right? There's a bunch of stuff that you can say. Okay, that's a lot of ads. Right. I can try with the third one too if you want, but I think you get the point. Be careful what you do. And Maybe I can try ChatGPT later. I will stop the recording here. Are there any questions?